Hello. Today we are going to go to chapter 3, and this is about measures of location. And remember, our first two chapters were about probability, and probability is the most fundamental object in statistics, and it was a way to summarize and describe the data. And this chapter and in the following chapter, we are going to learn averages and related things. Uh, an average is another common and fundamental way to summarize and describe data. So probability and average, these two are the major cornerstones of statistics. Roughly speaking, I think I can say we can say any statistics method is a kind of calculating probability or calculating a kind of average. Of course, a kind of is very broad and vague, but anyhow, you understand. Yeah, they are two most important concepts in statistics. So we are going to, by the way, you know what is an average. So yes, the average I teach is exactly the average you use in your daily life. So, but what I'm going to do is I'm going to extend the what role average plays in statistics, and we will study what is good about using average, but there are weaknesses. So and how we can extend the use of average in more applied situations. And chapters like I gave you here. So let me start with a more fundamental question. Can we calculate average? So you may think calculating on average is easy. Yes, it is easy, but we need to think about that again. So imagine there is a data set on, say, used cars. Used cars for sale, and it has these 5 variables: listed price, the make and model, and the model year, and mileage, and the number of major repairs. So, and we would like to calculate the average for each of the variable. Then, actually, one of the variable does not have an average. What is that? Yep. Okay, so the answer is B. Make and model has no average because, say, make and model is like Toyota Camry, like Ford, Chevy, like GM. So it is not a number. That's the problem. So to calculate the average, the variable must be a number. But the other variables like, say, price, year, mileage, number of repairs, the other variables are numbers, but the make and model is not a number. That's the problem. So we have in statistics, we call those kind of variables that that are not represented by a number. We call them categorical or qualitative variable, as opposed to quantitative. So you can think about it like in many examples. So for example, your major. So if I have data about students, and then the majors are like economics, business, mathematics, philosophy. So it's not a number. And what else? Like a lot of your nationality. It's not a number, right? Your gender, not a number. So a lot of things are not a number. But in this chapter, and from now on, all the remaining chapters, we are going to assume that all variables we are interested in are actually numerical. Like you may think it's like it's restrictive, but also it's not a big problem. Like we are going to see more examples later, and you know why we are doing this. We need to handle the variables more easily. Then numbers are actually more convenient to handle. And then once a variable is a number, then if the outcome is a number, we can calculate these guys. So not only average, but like maximum and minimum. Or like a maximum and minimum requires the outcome to be number. Uh, Otherwise, we cannot compare which is greater. And variance and standard deviation, obviously, variance and standard deviation should be like requires the variable to be a number, and median and percentiles. Like in other words, these are what we are going to study in this chapter and the following chapter. So, like in order to study those measures, we are going to assume numerical variables. And so, we, like in the random variable is the name we call for such a numerical outcome. So a random variable is a numerical description of outcomes from an experiment. In our previous chapters, in the probability and conditional probability chapters, it doesn't need to be a number. The outcome can be anything actually. Like it was about like man or women, or like high tuition or not. Like I gave you a lot of examples, like defective or not, domestic, foreign. So we consider the more abstract way of like outcomes, like by defining events. It's just a set of outcomes, and a set doesn't need to be a number, or like the elements of the set did not need to be a number. But now we are going to encode the outcome as a number. In many cases, the encoding is automatic, like coin toss. Coin toss has heads and tails, but you may put numbers on them. Like I'm going to call heads as 0 and encode tails as 1, or the other way. Does not matter. It's purely just an encoding for the computer to understand. So that's one possible way to understand a random variable. Or in other cases, the numerical description is natural, more natural, like dice. When you roll a dice, the outcome is already a number, the number of dots, right? So 1, 2, 3, 4, 5, 6. Or you may instead, like for example, if you want, you can call them 10, 20, 30, 40, 50, 60. Not a problem, as long as it is a number. And as long as you can understand. And YouTube video count, video view count. It's non-negative integers. It has like 0, 1, 2, 3, 4, 5. By the way, YouTube video counts are view counts are too low. So I guess like a view count algorithm is a little bit different. I don't think you didn't watch them, but I strongly believe YouTube has a different algorithm of counting your views. Anyhow, and stock return, it is also a number, like a 2% increase or minus 10%, like so 2 minus 10. These are numbers. So in statistics, a random variable is a numerical description of outcomes. And more mathematically, we define a random variable as a function from the sample space. Remember, the sample space to a set of numbers, right? That is so when I say random variable, it already implies it is a numerical outcome, numerical variable. So, from now on, I'm going to start from random variables all the time. When we think about randomness, I'll start with a random variable, say x, and they are usually denoted as x, y, z. And then probability is denoted this way. Automatic. It is a function, probability of x equals to something, or something like probability or random variable y smaller than or equal to something, right? So when it is exactly just like a sentence, and then what I want you to realize here is the different use of uppercase letters and lowercase letters. So uppercase letters denote a random variable. Like for example, like imagine the sentence that a probability that the number on the dice equals 6. And in this case, to define this probability, we equate two objects, the number on the dice and 6. We consider two objects and equate them. But the first thing, the number on the dice is like it can be anything. It can be any number between 1 and 6, right? So number on the dice is the random thing. We don't know what's going to happen. Just it's the future outcome. It's unrealized outcome, and it will realize only when you conduct an experiment and you observe it, right? On the other hand, lowercase letter, like lowercase x or lowercase y, plays this role. So, like to define probability, even if it's unrealized, to define a probability, you have to specify like something. Like in this case, for example, probability of the dice is not specific enough. You have to specify, we are interested in the probability that the result from the dice equals 6 or like greater than 3, for example. So like that, 6 and 3 are specific numbers, concrete numbers, and it is not random. It is just your interest. You are interested in that number, so it's just one possible value like it can take. So it's just right. So what I'm telling you is this is random, but this is not random. Well, like you have to distinguish what is random and what is not. And when obvious, I may shorten probability that random variable x equals to x as just probability lowercase x. So when the random variable is obvious, I may change it this way. And then, so for a random variable x, you repeat the experiment like a number of times, usually denoted as n. That's the sample size, repetitions. If you repeat the experiment, we are going to denote the realizations this way. X subscript 1, X subscript 2. So in the first experiment, you observe x1. In the second experiment, you observe x2. And the last experiment, you observe xn. So this is the typical standard notation in statistics for a random variable and its realization, which is the data, right? So in statistics, our data will be denoted this way. Okay, so this is a basic setup, preliminary setup to calculate average. So we learned to calculate an average, the outcome must be numerical, and we call this as the random variable, and we defined some notation. So then I'm going to start why we need averages with an example. See you in the next video.